Use case of one smart intersection with VRU detection is one of the scenarios showcasing real-time, low-latency safety enhancements in connected transportation. Led by Marmara University, it focuses on real-time responses and alerts, multi-intersection coordination, and adaptive traffic management. The DECICE framework enables easy deployment, smart scheduling, energy-efficient computational orchestration, and dynamic adaptation to changing conditions of edge cloud applications for this use case scenario. This slide illustrates the processing pipeline for VRU detection at smart intersections. Camera frames are sent to an inference application, which processes them on dynamically scheduled edge cloud nodes. The key constraints are that the camera-to-inference delay must not exceed 100 milliseconds, and the total camera-to-RSU delay must remain under 300 milliseconds to ensure real-time safety responses. Marmara's edge on-prem infrastructure includes cameras, roadside units, routers, and x86 ARM nodes, supporting dynamic workload deployment. Additionally, network delays can be simulated between devices to test real-time performance and optimize latency-sensitive applications. Cluster nodes executes the workload of the scenario. The jobs will stream live video from cameras to detect road users and to send V2X messages. In this scenario, two jobs are already running for intersection 1 and intersection 2. A new job is submitted to process data from intersection 3. Scenario 2 is similar to Scenario 1, but the latency from the Jetson Orin devices to the cameras is artificially increased using the Linux traffic control tool to influence the use case 1 ILP scheduler's decision when assigning the new job, as it will now need to account for this added latency into its decision. The integration of DECICE framework components is illustrated in the DECICE framework control manager diagram above. Jobs can be submitted via the web dashboard, and the platform-specific glue code component will create the corresponding workloads in the underlying compute plane, such as Kubernetes. Running workloads can be viewed from the dashboard, and the kubectl CLI can also be used to list DECICE jobs, custom Kubernetes resources, in the compute plane. New jobs, such as Kubernetes workloads, can be submitted via the dashboard, and the platform-specific glue code will create DECICE jobs custom resources along with other necessary resources. Initially, workloads will be in a pending state, awaiting scheduling by the DECICE framework. For pending workloads, platform-specific glue code requests a scheduling decision from Control Manager. In turn, Control Manager starts the scheduling workflow and sends a request to the PromQL to JSON wrapper to populate the digital twin with the metrics from Prometheus. Prometheus Node Exporter is used to collect metrics from every node in Cloud Edge Continuum. Custom network exporters are developed to collect node-to-node and node-to-device network metrics, such as latency and bandwidth, from each cluster node. These metrics are also stored in the Prometheus. To reduce the amount of metric measurements, nodes and devices are grouped together, and measurements are only made between these groups, called vertex pools. In the current implementation, vertex pools can be thought of as similar devices within the same LAN. The PromQL to JSON wrapper populates the digital twin with node metrics, devices, network metrics from Prometheus, and DECICE jobs from the job database. The cluster is then represented by the cluster state, ready to be used by the scheduler. Next, in the scheduling workflow, after the digital twin is populated, the control manager triggers the scheduler controller. The scheduler controller makes a scheduling decision using the DECICE scheduler and digital twin, and then scheduling decision is realized in the compute plane by the platform-specific glue code. Next, the adaptive scheduling capability of the DECICE framework is demonstrated with two scenarios. In both cases, two workloads are already running on two nodes, while the other nodes remain idle to conserve energy. The key difference between the scenarios is network latency. In the first scenario, there is approximately 10 milliseconds latency between Orin nodes and cameras. The scheduling decision once again places the new workload on an Orin node that is already running a workload. As a result, other nodes remain idle, conserving energy, but at the cost of increased inference time, though still within a tolerable range, for applications running on the occupied Orin node. The occupied Orin node's metrics increase with the added job. For the second scenario, the delay between orans and cameras is artificially increased, resulting in approximately 40 milliseconds latency. This time, the scheduling decision assigns the job to an idle nano device since the scheduler and framework account for network metrics between nodes and job characteristics. Since the increased latency between ORAN nodes and cameras would no longer be tolerable if a second job were scheduled on an occupied ORAN, the scheduling decision results in waking up an idle nano node with better network latency.